Okay, in the last section we learned about log rules, specifically the product, quotient, and power rule. In this section, we're going to move on and start talking about solving logarithmic equations and how we can use those rules to help us solve equations, logarithmic equations. So we want to start by identifying what a logarithmic equation is. So remember, the definition of an exponential equation was any equation that has a variable in the exponent. A logarithmic equation would be any equation that has a variable inside of a logarithm, inside the power of a logarithm. Okay, and so here is our primary rule for the day. If we have two logarithms with like bases that are equal to each other, then the powers, the numbers inside the logarithm, would have to also be equal to each other. Okay, really, I think hopefully intuitive and simple and straightforward. If we wanted to see how is this true algebraically, you could think about, we know that in order to solve equations, we always solve using inverse operations, right? So suppose I had something like log x equals log 2. It's obvious that x would have to be equal to 2. How is that happening algebraically? Well, really, when we say log x, we mean common log, or log base 10. And to solve equations, we use inverse operations. So the inverse of log base 10, you'll remember we described the log function is the inverse of the exponential function. So if I have an exponential function 10 to the x, its inverse is log base 10 of x. Right? These guys are inverses of each other. So if I have log base 10 and I want to undo it, I'll apply it as a power of 10, and the log base 10 and base 10 cancel each other. So right here, if we wanted to solve this equation over here, really we're just raising both sides as powers of 10. And the log base 10 will cancel the 10, and we'll be left with x equals 2. So that is algebraically why this rule is true. It's not a huge deal that you follow that necessarily. Hopefully it's pretty straightforward, but what is the important takeaway is that if you have two logarithms with like bases that are equal to each other, then the powers would have to also be equal to each other. And all of this logic that I said over here would all be equally true if I had had 3 as the base, right? Log base 3 of x is the inverse of 3 to the x. So if I raise 3 to the log base 3 power 3, base 3 and the log base 3 cancel each other. Same for any base, 10, 3, e, whatever base you could have, this property holds the same for any base. Particularly common logs and natural logs. Those are the most important ones for us, but it's true for any base. So let's look at some examples. We'll start with a real straightforward one here. Log base 3 of x plus 4 is equal to log base 3 of 6. You'll notice we have like bases. We have a single log on each side, so if we have a log with the same base equal to a different log with the same base, then the powers have to be equal to each other. So x plus 4 would be equal to 6. From there, we're just using regular inverse operations, and we see that x is equal to 2. Okay, so when we have a single log set equal to a single log, really simple, really straightforward, just set the powers equal and solve. Okay. Let's do another example where where we don't have a single log equal to a single log. So this is where we have to use our rules that we've been talking about in the last section. So this is example 2 here. It says log 12 minus log x is equal to log 3. So here on the left side we have two separate logarithms, and in order to use our rule we have to have a single log equal to a single log. So what we need to do first is condense this left side into a single logarithm. Specifically, the fact that I'm subtracting these logs tells me I'm going to use the quotient rule. So log 12 minus log x by the quotient rule is really equal to log of 12 over x. So now that left side is a single logarithm. So I want to use my product quotient power rules, whichever ones are available to me, or are relevant to the problem, to condense the multiple logs so that I have a single log on each side. Once I have a single log, and these are both common logs, so we know they're both base 10. Once we have a single log on each side with like bases, we can simply set the powers equal to each other and then use inverse operations to solve from there. So 12 equals 3x, divide by 3, and x equals 4. Okay. So to summarize that, what we actually did there, we said if we don't have a single log on each side, then we're going to go ahead and condense both sides so that we have only one logarithm on each side of the expression, right? In this case, we use the quotient rule, but this condensing is going to be using our log rules. So we might say using the product, power, and quotient rules from the previous section, which is why we need those rules, right? In the last section might have felt like we're just doing these random exercises with all these substitutions, and really the point was to make sure we're really strong with those rules so that we'll be able to solve logarithmic equations. Okay, so here's our steps. Condense both sides so that you have a single log on each side. Then you can set the powers equal and solve for the variable. Let's do one more in this video. We'll split this section into two videos here. In this last one, similar problem, but now we have two different logs on both sides. But notice all four logarithms are natural logs, or log base e. So since we have common bases for all of our logarithmic expressions here, we can use our product, power, and quotient rule to combine sides into single logarithms. So if I have natural log of 10 plus natural log of 3, that means I can use the product rule and say that's really natural log of 10 times 3 on the left side. On the right side, again, I have two logs being added, so I can use the product rule. But be careful here, it's x plus 2 times 5. I'm going to write it this way to be a little clearer maybe. So that right side would become natural log of 5 times x plus 2. From there I could distribute inside of that right logarithm. So I'd have the natural log of 5x plus 10. On the left side, 3 times 10 is 30. And now I see I have two different natural logs set equal to each other, which means the powers inside those logs have to be equal to each other. So I can just set those equal. 30 equals 5x plus 10. And how do we solve equations? Isolate the variable by performing inverse operations on both sides. And we get back down to x equals 4. So same as the previous example, that's just coincidence, right? So solving logarithmic equations, we want to make sure we get down to a single log on both sides. Once we have a single log on both sides, we can set the powers equal to each other and solve from there. If we don't have single logs on both sides, we have to combine and condense each side so that we have a single logarithm on both sides before we can go ahead and actually set the powers equal to each other, right? So condense both sides, set the powers equal to each other, solve the equation. All right, we'll pause here. In the next video, we'll do some more examples and look at some of the different types of things that could come up in logarithmic equations.